Hello and welcome back. In this video we're going to learn how to find the length of a polar curve. We can find it by taking the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. That integral should look somewhat familiar, vaguely familiar, and we're going to derive it at the end after example 4. But for now, you can just take this as the formula for finding the length of a polar curve from theta equals alpha to theta equals beta. Note, as usual, that as you go from theta equals alpha to theta equals beta, the curve must be traversed exactly once, otherwise you're going to be double counting or triple counting the length of the curve. So in example 4, we're asked to find the length of the cardioid r equals 1 minus cosine theta. This is shown in figure 6, just for reference, but we're not going to need it. What we're going to need is dr d theta, because that's what we need to plug into our arc length integral. Dr d theta is going to be sine theta. So the length of this polar curve will be the integral across the whole curve, which will be 0 to 2 pi. 0 to 2 pi will get you all the way across the curve, of the square root of r squared, that's 1 minus cosine theta squared, plus dr d theta squared, which is sine theta squared, d theta. Let's try to take this one all the way to the end, because there's a little bit of trickiness going on with this integral. When we expand out, we'll get 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. I see a cosine squared plus sine squared. That's going to get turned into 1. So then we get the square root of 2 minus 2 cosine theta d theta. Now this integral is a little bit tricky. You could try doing substitution, but you're going to struggle there because there's not like a sine theta there with the d theta. You could maybe try doing another u substitution where you let u equal the whole radical. I suppose you could give that a try as well. Here I'm going to take the strategy of trying to find a trig identity to help us out. If we factor out this 2, we're going to have a 1 minus cosine 2 theta. Let's actually do that off to the side. Factor out the 2 and we have 1 minus cosine theta. And the reason 1 minus cosine theta is so interesting is because that seems like the top part of some trig identities, right? There's like 1 minus cosine 2 theta over 2, for example. There's also the half angle formulas where you have plus or minus the square root of 1 minus cosine theta over 2 as well. So here we're going to make use of that. Here we're going to rewrite the 1 minus cosine theta. We're going to put a 2 underneath there. Now we can put a 2 underneath there by dividing by 2 and multiplying by 2 inside of the radical. So this will give us 4 times 1 minus cosine theta over 2. Now if that looks like dark magic, just take a moment to step back and try to simplify this. Here a 2 would cancel and we would get back 2 times the 1 minus cosine theta, getting you back to where we started from. So we can take this step, and the whole reason we're taking this step is to put a 2 underneath the 1 minus cosine theta over 2. Okay, so here we can make use of the half angle formula. Just as a reminder on the side, we can think of it as sine theta over 2 equals plus or minus the square root of 1 minus cosine theta over 2. But we're just squaring both sides, so we get sine squared of theta over 2 equals 1 minus cosine theta over 2. So we can replace 1 minus cosine theta over 2 with sine squared theta over 2, Now the whole reason for going down this road, and here you do have to look many steps ahead, but now that you've seen the trick, you can remember how it works. The whole reason for going down this road was to collapse the minus and just write everything inside as a perfect square. Right? 1 minus cosine theta over 2 can be rewritten as a sine squared, which is great because then we're going to get rid of that radical that's causing the integral to be so hard to do. So we're going to get 2 sine theta over 2. One thing we should mention and worry about is this really like 2 sine theta over 2, or is it the absolute value of 2 sine theta over 2? Because when you take the square root of x squared, technically it's the absolute value of x, unless x is positive, in which case you can drop the absolute values. So let's see if sine theta over 2 is positive. And it is. If sine theta over 2 will be positive when theta is between 0 and 2 pi. Right? If theta is between 0 and 2 pi, theta over 2, which is what's inside our sine, is between 0 and pi, and sine is positive there. Sine is positive when theta is between 0 and pi. That's the first and the second quadrants where the y values are positive, so sine is positive. So that's good. We don't have to worry about the absolute value bars there. So this whole integrand collapses into just 2 sine theta over 2. From here, it's not too bad. I'm going to put a little dot 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 from here. You'll get 8. Here you'll have like a mental u substitution, so when you integrate sine theta over 2, you'll get negative 2 cosine theta over 2. And then this extra 2 will be in front. And then you can plug in the limits of integration and evaluate it to 8. So the 8 represents the length around this polar curve. Not the area inside of it, but the distance around this polar curve if you had to walk around it. So we mentioned that we were going to explain why the integral for the arc length of a polar curve is the way it is. So what you can do to get that is ride on the fact that you can rewrite polar curves using a parameterization. So we can parameterize the polar curve by using x equals r cosine theta and y equals r sine theta, where r is a function of theta. We did the same thing in the last section where we were trying to figure out the slope of the tangent line of a polar curve, and we used the parameterization to help us out. Same thing here. So if we take this as it is, and we think of r as some kind of function of theta, we can differentiate x with respect to theta using the product rule. So we'll get the first times derivative of second plus the second times derivative of first. And switching the two terms around, we'll get dr d theta cosine theta minus r sine theta. First times derivative of second will give us the negative r sine theta. And then the other one will give us the dr d theta cosine theta. We can do the same thing for y. Find dy d theta by taking the derivative with respect to theta and using the product rule. We end up with something like this. Then if we look at dx d theta squared plus dy d theta squared, which is what would go inside of the arc length integral for parametric curves, then here's what we get for our dx d theta and dy d theta that we just figured out here for our polar curve. Well, it's a bunch of messy algebra. Basically, you have to square this whole thing, and that's the first 3 terms. Then you have to square dy d theta, and that's the second 3 terms. And then a whole bunch of stuff cancels and collapses, or gets put together. If you notice, there's a dr d theta squared cosine squared theta and a dr d theta squared sine squared theta. If you factor out the dr d theta squared, you'll get a cosine squared plus sine squared, which is 1. So those two terms become dr d theta squared. The minus 2r dr d theta cosine theta sine theta thankfully cancels with the positive version of itself. Otherwise, that'd be a big giant mess. And then the r squared sine squared theta and the r squared cosine squared theta, you can factor out the r squared, and what's left turns to 1, and you just get r squared. So what goes inside of the radical using the arc length for parametric curves, what you get is just r squared plus dr d theta squared. So what goes inside the parametric version ends up being, in the polar version, r squared plus dr d theta squared. So that explains why we have that formula for the arc length of the polar curve. Thanks so much for watching, and see you next time.